Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIUA campus. In this video, we will discuss the LTI system properties in details. Okay, let's move towards the properties of LTI systems. As you know that LTI systems can be characterized completely by their impulse response. It means that if you know the impulse response, you can characterize the LTI system very well. So the properties can also be characterized by their so similarly the properties can also be characterized by their impulse response as well. So let's see the first property, which is the commutative property of LTI system. So these all properties are very much important to solve the convolution problems in the literature, and it will be helpful for problem solving. For example, a property of convolution in both continuous and discrete time is a commutative operation. As you know that commutative means that if the position of one variable is changed, it doesn't affect the result. So in this case as well, for convolution, if you change the position of the variables xn and hn, then it will not affect. For example, xn equal to hn is equal to xn into xn as well. So xn hn, you get yn, and hn to xn is similarly you get yn. The other property is the distributed property of LTI systems. In this property, as you already studied in the mathematics several times, what is distributive property? So we will apply the same property here for the convolution as well. So for both discrete and continuous time systems, this property means that summing the outputs of two systems, like summing the output of two systems, is equivalent to the system with an impulse response equal to the sum of the impulse response of the two individual systems. For example, this one, xn into h1n plus xn into h2n. So distributive property of convolution can be exploited to break a complicated convolution into several simple ones. For example, if you have a complicated convolution type of questions, then to solve them to easily solve them, we can break them by using the distributed property. So this is the block diagram to just show the output. For example, x here h1, x here h2. So x into h2, x into h1. So x into h1 plus x into h2. So for the other side, x into h1 plus h2. So x into h1 plus h2. So we can write this property as here as well. So example of a distributed property. For example, if you have an LTI system and that has an impulse response un, like you know that this is your input, right? When you input the signal, for example xn, which is impulse, right? If you input the signal, which is impulse, and output you got is the impulse response. So in this case, the impulse response is u of n, right? So the impulse response of a system is un with, whereas the input is xn is equal to half n u n plus 2 n u minus n. Now you can see that the sequence xn is non-zero along the entire time axis, right? So direct evaluation of such convolution is somewhat tedious. Instead, we may use the distributed property to express yn as the sum of the result of two simple convolution problems. For example, you look at this. If you have a xn, only one xn here, and you want to convolve this one, this will become difficult because of addition and number of things. Now you can break them into two parts. For example, you can break this part into x1 of n, and you can break them into x2 of n. For example, x1 of n, x2 of n, using the distributive property. Then you just using this distributive property, like x1 into ht, x2 into ht, you can get y1n, y2n, which is equal to, when you sum this result, then you will get y of n. So this is the example of a distributed property. The other property is the associative property of LTI system. As you know that associative property in mathematics as well. So here the same thing but for the LTI system. So the change of for LTI system, what does it mean? The change of order of the cascaded systems will not affect the response. For example, if you have x here and you have h1 here and you pass through this system, then you will get the output, which is the convolution x into h1, and then you pass this input to the system which has an impulse response h2, then in the end you will get x1 into h1 into h2. So in associative property, it means that x is into h1 h2, this one x into h1 h2, and commutative is h2 into h1. As you know that the convolution is a commutative property as well. So you can write h1 h2 into h2 and h1 as well. So you can get x into h2 h1. Just the order is changed, right? So for the associative, so x into h2, x into h2 into h1, so x h2 into h1, right? So you can see that these two are commutative operation. Sorry, is associative property. It follows the associative property. So by changing the order, like previously there was h1 here and h2 here. Now there is h2 here and h1 here. So the result will always be same. Let's discuss another property, memory. An LTI system with impulse response H is memoryless if and only if Ht equals to 0 for all t not equal to 0. As you know that impulse response means that we will input the impulse to the system, then the output of the system is called the impulse response. So you know that when we input the impulse, so impulse is the one only at time 0, right? So it means that whenever for all t not equal to 0, ht should be 0, whereas ht should be 1 when time is 0. So that is, an LTI system is memoryless if and only if its impulse response is of the form ht equals to k delta t. So where k is a constant. Here k is constant and delta t. It means that impulse response only depends on the current time, which is time t equals to 0, and for other time it is equal to 0. Consequently, every memoryless LTI system with input x and output y is characterized by an equation of the form. So it was bit specific, and for more general type of a memoryless system, it is represented as y equals to x. X is your input and this is your impulse response, as we already derived here. So input into impulse response is equal to k of x. So any system is memoryless if when we input x, in the output we get the scaled version or the amplified version of x, but there is a no delay or something else, right? So k is a constant term and x is your input. So that is, the system is an ideal amplifier. So it is kind of an amplifier. When the system is kind of an amplifier, it is a memoryless system. So for LTI system, the memoryless constraint is extremely restrictive, as every memoryless LTI system is an ideal amplifier, right? Causal. As we already studied, causal means that there is no output before time equals to 0, right? So similarly for LTI system with an impulse response H is causal if and only if Ht equals to 0 for all t less than 0. Less than 0 means when before 0 there is no output, right? Then H is, that is H is a causal signal. It is due to the above relationship we can call a signal X satisfying that Ht is 0 for all t less than 0. So when Ht is 0, so it means that for a system when we apply to any output to any system, LTI system, the input should be 0 before time equal to 0 to be a causal signal. Similarly, for invertibility, this is another property. Invertibility means that if you have a system, then if a inverse of that system exists, then it is called an invertible system, LTI system. So the inverse of LTI system, if such a system exists, it is an LTI system. So let H is the impulse response of a original signal system, and H inverse denote the impulse response of a LTI system and its inverse, right? And H inverse is the LTI system response of the inverse of the LTI system. Then when you multiply H with H inverse, then it should be delta. Delta means 1. What does it mean? H into inverse means H minus 1, right? R equals to H into 1 over H. So when you multiply H with 1 over H, you should get, because 1 over H is inverse, H will cancel out and you will get 1. R1 means delta, right? So then it is called an invertible system. So consequently, an LTI system with impulse response H is invertible if and only if there exists a function H inverse such that delta exists, right? Except in simple cases, the above condition is often quite difficult to test, right? When there is a impulse response is simple, like for a u of t and something function like that, which is easy to solve, but usually it is very difficult to test this result. Like we have to find the system impulse, then inverse of impulse, and then verify with that it is invertible or not. Stability. It is very important to test the stability of a system. If a system is LTI system is not stable, then uh, you can say that it is, if it is not satisfying the property, then it's not a good way. So a LTI system with impulse response H is bounded input bounded out to stable if and only if you take the absolute of a impulse response, right? This is impulse response H of t, and then you take the absolute and then integrate, and if this integration is less than infinity, then it means that you have the system is stable because it is absolutely integrable. Absolutely integrable means take the absolute and then integrate, and then if it is less than infinity, it is called an absolute integrable. This is for continuous time case, and for discrete time there should be summation here. So you can see that the stability depends on the impulse response, right? Now, previously in last slide we saw that uh, the system will be bibostable when when h of tau or t is less than infinity. It means that the absolute of the impulse response is less than infinity. Now we have want to prove that equation here as well. For example, you have a bounded input. So bounded input x of t, and then you will take absolute of that one. So absolute should be less than b, right? Absolute means its amplitude, the absolute value is less than b for RT. This is input, given input, right? And whereas we also consider that yt is less than a for RT. Like this is your input and this is your output. Now let's convolve them. So you know that yt equals to uh, h of t or h of tau xt minus tau theta. So by using the commutative property, because usually xt is here and ht minus tau is here, but we can commute because of the commutative property for convolution. So there will be no difference in result, but this will help us to simplify the equation easily. Then take the absolute, because for amplitude. So yt absolute and then absolute here as well. And, now less or equal to sign appear here when we move the absolute from uh, outside to inside. Like now you see that ht absolute x absolute of xt minus ta and then deta. How y is less or equal to due to this property a plus b absolute whole absolute is always less than equal to a absolute plus b absolute. For example, if you take a equals to 1 and b equals to 2, then both are 3 3, right? So it is equal. But for example, if you have a equals to minus 1, b equals to 2, then when minus 1 plus 2, you will get here the result 1, right? Whereas when you put here a absolute means minus 1 absolute always 1 plus b absolute 3 2 absolute will be 2. So 2 plus 1 will be 3. So 1 is less or equal less than 3. So it means that uh, this equation will always less or equal to 3, not equal to, not always equal, right? So that's why we introduce less or equal to sign here, right? It is minus infinity to infinity. Now we know that xt amplitude is less than b. So by introducing the delay, it will not affect the amplitude, right? Only the time delay. So it can be equal to, it will be equal to x t minus t equals to b, right? So put b here, right? And then you will get yt equals to less or equal to t x h of t b, right? And after simplifying more by putting h of t, which is a, right? Which is then if you get y of t absolute, then the result is less than infinity. So when it will be infinity, if and only if h of ta less than infinity. So if it is not less than infinity, then yt can't become less than infinity. So we concluded that for a bistable system, right? For a bistable system, it will be uh, stable when impulse response is less than infinity. Instead of doing some multiplication like involving x and h, we only need to test h of ta and absolute take absolute and then integrate, and if its result is less than infinity, it means that the system is bistable. Now let's take an example for this bistability. The picture is not much clear, but I think it is clear enough to read the text, right? Consider a system that is a pure time shift, pure time shift in either continuous time or discrete time. For example, in discrete time, as I mentioned that the condition is but h star d star h star absolute, right? D star minus infinity to infinity and should be less than infinity. This is for continuous case. Whereas for discrete case, it should be n equals to minus infinity to plus infinity absolute of h of n, and it should be less than infinity. Here we first we are taking the in what we say that we are taking the discrete time case. So for discrete time case, n equals to minus infinity to plus infinity h of n, which is for h, as we are considering the pure time shifter, right? It means that we are inputting, we have our impulse response is a pure time shift. Pure time shift means that delta n minus n naught, your amplitude is your signal is delta n minus n naught. So by doing these shifts, if you then take the summation, you know that delta is only 1, will be only 1 at delta n naught, n minus n naught. So it will only give you 1 at n equals to n naught, and for other values it will be 0, right? So other values it will be 0. So this summation doesn't affect. So result will be 1. So you see that 1 is less than infinity. So it means that it is bounded input, bounded output stable. While in continuous case, same h star minus t infinity to plus infinity, minus star infinity to plus infinity, delta t minus delta tau minus t naught, it will be 1 only for t naught. So the result will be 1. So it means that it is bounded stable. And we conclude both of these systems are stable, and this should be not be surprising, since if the signal is bounded in magnitude, so is any time say shifted version of that signal is also bounded. You know that delta t is bounded because uh, when we input delta t, output is always 1, right? So similarly, if we input the shifted version of delta t, it is nothing else except the delay. So it will also be bounded. Now consider the unbounded example. Now consider the accumulator described before as well. As we discussed in section 1.64, this is an unstable system. Since if we apply a constant input to an accumulator means it is a kind of a summation type of a system, like it accumulates the system, right? Outputs. So the output grows without bound. It accumulates, then output grows without bound. Thus, this system is unstable, and it can easily be seen from the fact that its impulse response, the impulse response of a accumulator is that, for example, n is equal to minus infinity to infinity. Here, the impulse response is u of n. So when we u of n, then take the absolute. So because of u of n, the limit will change from 0 to infinity. And now you can see that for u of n is for each value it's 1, right? For example, n is equal to 0, it's 1. U of 0 is 1, right? U of 1 is 1, and u of infinity is 1, so on up to u of infinity is also 1. So it means that it will grow till infinity, because if you add the infinite number, the result will be infinity. So it means that this is not a stable system. Now take another example. Consider the integrator, the continuous time counterpart of the accumulator, because in accumulator is in discrete time, and similarly integrator we called integrator in continuous time. So for minus infinity to infinity x star theta, this is an unstable system for previously the same reason as that given for accumulator, that is constant input gives to an output that grows without bound. So the impulse response of an integrator can be found that by letting xt is equal to delta t, because when you your input is delta t, so delta t, then take the absolute and integrate. If you will integrate the delta t, you will get the impulse response, which is u of t, because integration of delta t is u of t. Now it uh, after finding the impulse response, now you integrate the absolutely integrate the impulse response. So now you have to integrate u of t absolute delta t dt deta, sorry. So limit will change from a minus infinity to 0 to infinity dt, and by integrating u of t you will get the infinity, as before for the we have seen for the accumulator. So similar is the case for the integrator. Since the impulse response is not absolutely integrable because it is not less than infinity, so system is not stable. So in this way, we concluded that by verifying the impulse response, absolutely integrable impulse response, we can see that whether the system is bistable or not. So this is all from the properties of LTI system. Thank you for listening. And for question answer session, there will be some reserved slot. So exact time will be communicated later on. Thank you.